Here we are given that the mass of a radioactive substance decays at a rate that is proportional to its mass. And this is given in terms of differential equation as this one that says dm over dt equals negative k times of m. So this is a differential equation involving the variables m and t, and we have to solve this equation. So basically we have to find this equation m of t, which represent the mass of the radioactive substance. So let's see how to do this one. So first we have to separate the variables. So I'm going to first divide by m and multiply by dt. So when I do that, I get dm over dt, and this equals negative k times of dt. So now we can see that we have separated the variables. That is all m and its derivatives on the left side, and all t and its derivatives on the right side. And once we have separated the variables, we integrate both sides. So we integrate integration of dm over m, and this could be considered as 1 over m dm. So basically we are integrating 1 over m, and I can factor this k, which is a constant, that is it is a negative k. I factor this negative k out of the integral, and we just have dt. So let's integrate this. Integration of 1 by 1 m is natural logarithm of m, and this equals negative k integration of dt, which equals the integration of 1 dt, and this is t. We also put the integration constant c. Now this is equation or a kind of form with m of t, but we have to solve for m of t, so I'm going to exponentiate on both sides. So I do e raised to the power of natural logarithm of m, and this equals e raised to the power of the whole quantity. Now we know that e and natural logarithm are inverse to each other, so therefore they cancel out. So on the left side, e and natural logarithm m cancel out, which gives the expression m, and this equals here we have e raised to the power of negative kt plus c. So we can write down this in form of m of t. So this is the expression or the function representing the mass of the radioactive substance. That is, m of t equals e raised to the power of negative kt plus c. But here we have to determine the value of c. So for this, I'm going to use this initial value, that is t comma m equals 0 comma 30. That is at t equals 0, m of t equals 30. T equals 0, m of t, which is m of 0, and this equals 30. So let's plug in t equal to 30 into this function, and when we do that, we get m of 0, and this equals e raised to the power of negative k times of t 0 plus c. I'm sorry, this has to be with the exponentiation plus c. Replace m of 0 by 30. So therefore this equals 30 equals e raised to the power of this is 0. 0 plus c is c. So we are getting e power c equals 30. And we can also determine the value of c by taking natural logarithm on both sides. So when we take natural logarithm on both sides, we get natural logarithm of 30, and this equals natural logarithm of e raised to the power of c. Using the power rule of natural logarithm, we can put this c in front. So therefore, this becomes natural logarithm of 30, and this equals c times of natural logarithm of e. Remember that the natural logarithm of e is a constant, which is 1. The value of natural logarithm is 1. So when we replace this by 1, we get c times of 1, which in fact is c. So I'm just going to put c over here, and this equals natural logarithm of 30. So we found the value of c, which equals natural logarithm of 30. And so we plug in this value of c into the m of t function. So let me do that. I write m of t, and this equals e raised to the power of negative kt plus c is natural logarithm of 30. Now I can split this exponentiation on the right side into two parts. That is using the exponent clause. That is, if we have a raised to the power of m plus n, this can be written as a raised to the power of m times a raised to the power of n. So similarly, here I have this exponentiation e raised to the power of negative kt plus 30. So one of them I can consider this as m and this one as n. If I use this rule, then this can be written as e raised to the power of negative kt times e raised to the power of natural logarithm of 30, and we can cancel this e as well as this natural logarithm as they are inverse to each other. So we just get only 30 for the second term. So this means we can put this as e raised to the power of negative kt times 30, or we can put this constant 30 in front and give it in the form 30 e raised to the power of negative kt. So this is the final expression which represents the m of t. So m of t equals e 30 e raised to the power of negative